Welcome to all of you. Paper CC-10 Semester 4 Mathematics Honours Year 2022 MCQ question number 1. Question 1a. A system of coplanar forces has total moments h, 2h and 3h about the points 0, 0, 0, 1 and 2, 4 respectively. Then the equation of the line of action of the resultant is, correct option is 2, x minus y equal to 1. Here the answer. If G dash be the algebraic sum of the moments of the system of the forces about any point D with coordinates h, k, then we know G dash equal to G minus h capital Y plus k capital X, where capital G is the moment about O, capital X and capital Y are the algebraic sum of the result parts of the given system of forces along OX and OY axis respectively. Here G equal to capital H, because here given in the question moments with capital H about the origin 0, 0. So here G equal to capital H, and about the point 0, 1 moment is 2h. So G dash equal to 2h when we find the moments about the point 0, 1. So 2h equal to h minus 0 capital Y plus 1 into capital X, equation number 2, and the moment 3h about the point 2, 4. So we get from 1, 3h equal to h minus 2y plus 4 capital X, equation 3. Solving 2 and 3, we get capital X equals to capital H and capital Y equal to capital H. And the equation of the line of action of the resultant R, capital R, is small x capital Y minus small y capital X minus capital G equals to R. This is the equation of the line of action of the resultant R. So here capital Y equal to H, capital X equals to H, and capital G equals to also H. So putting all these values in this equation, we get small x minus small y minus 1 equal to 0, that is x minus y equal to 1 is the required equation of the line of action of the resultant. So option, correct option is 2. And the value of the resultant R, root over of capital X square plus capital Y square, that is equal to root of 2 into capital H. Next question 1b. The condition for equilibrium of a particle constrained to rest on a rough curve under any given forces with usual notations is, correct option is 2, capital X plus capital Y dy dx whole square less than equal to mu square capital X dy dx minus y capital Y whole square. Here, this is the curve. This is the curve, and this is a tangent. T, P is the point with coordinates x, y, and this is the x-axis and this is the y-axis. And let the particle be rest at the point P of the rough plane curve, and this is the tangent, and this is the friction force F in this direction, and capital X, capital Y corresponding the result part of the system of the forces along the x-axis, along the y-axis, and this is the PN is the perpendicular uh, on the tangent PT, and this is the R, force R is the normal reaction. So resolving this force capital X, we get this angle is phi with the x-axis with the tangent PT. So capital X can be resolved by along PT is the x cos phi, and this in this direction opposite to PN is x sin phi. So resolving the forces and F. So along the direction PT, we have three forces: uh, x cos phi plus y sin phi plus capital A equals to 0. Because this y sin phi comes from this force y, result part of y along PT is the capital Y sin phi. And along the normal PN, the resolving the forces along the normal PN, here R is the normal reaction, and corresponding capital Y cos phi is the component of Y along this direction PN, and component of X uh, opposite to PN is this X sin phi, so this is the minus X sin phi equals to 0. And here from 1, capital F equals to minus x cos phi minus y sin phi, and capital R from 2 equals to x sin phi minus y cos phi. And for equilibrium position, and obviously magnitude of F is less than equals to mu magnitude of R, normal reaction. Force of friction is less than equals to coefficient of friction into the magnitude of the normal reaction. Squaring on both sides, f square is less than equals to u square r square. So putting the values of f square and putting the values of r square, and this after dividing cos square phi on both sides, we get x plus y tan phi whole square less than equal to u square x tan phi minus y whole square. And also dy dx equals to tan phi. So putting this value dy dx tan phi, and we get the result. Equation correct option is 2. Next question C. Which of the following forces do appear in the equation of partial work? Correct option is to weight of a body or of a system of bodies, because option 1, option 3, and option 4 don't appear in the equation of the partial work. If capital W with the weight and small x with the distance of the center of gravity of the body or of the system below some fixed plane, the virtual work done by the weight due to a small displacement is W delta x. But if x be the height of the center of gravity above some fixed plane, then the virtual organ is negative, minus W delta x. So obviously, weight of a body or of a system of bodies obviously present in the equation of the virtual work. But the other options, the force of action and reaction between two particles, when the distance between their remains invariable, or option 3, the reaction of a smooth surface when the body in contract if it slides on the surface due to displacement, and the reaction of a fixed surface when the body is in contact it rolls without sliding on the surface due to displacement do not appear in the equation of the partial work. Next question 1D. A uniform ladder rests in limiting equilibrium with its lower end on a rough horizontal plane and its upper end against a smooth vertical wall. If theta be the inclination of the ladder to the vertical and mu be the coefficient of friction, then the correct option is tan theta equal to 2 mu. Here PQ is the ladder with length twice A, uniform ladder with length twice A, and S is the center of gravity of the ladder. So ASQ equal to A distance A and SP equal to distance A. And here the vertical wall, along the vertical wall is y-axis, say, and the horizontal floor is the horizontal lap plane along the x-axis. So at the point P, we have two forces is mu r along this direction PO and the normal direction R. And mu r is the frictional force on this P because this surface OX is rough horizontal plane. And here the point, contact point Q of the ladder on the vertical plane, which is smooth. So here only the normal direction R dash along this QO dash. Now, here we and theta is the angle, here is the inclination angle of the ladder to the vertical. So theta is the angle this angle is theta. So obviously this angle is theta, this angle is theta, and this. Now, when theta is greater than lambda, then theta is greater than lambda, the for the equilibrium we can resolve the force in direction x and y. We get R equal to W and R dash equal to mu r. R dash equal to mu r. Here lambda is the angle of friction. Here angle of friction. Angle of friction means the perpendicular normal direction and the frictional force, and the resultant is this P O dash. So the angle between the resultant force of the normal direction and the frictional force with the normal direction is the angle lambda, is the angle of friction. Obviously, this ladder is in equilibrium, limit equilibrium. So obviously, this normal direction R and this is the weight of the ladder which acts from the S point CG of the ladder, S, W is downwards. So obviously this W downward direction and this the perpendicular normal direction, upward direction, both are equal. And R dash is the normal direction at the point Q, the direction along the x-axis, and obviously this equals to mu r. Mu r is the opposite to the direction of x-axis, mu r frictional force. So obviously on the position of equilibrium, these are dash force with the equal to the mu r force. Obviously, mu is the coefficient of friction. Now we taking the moment about the point P, we get so about the point P, this mu r force passing to the point P and this normal direction R passing to the point P. So moment about P of these forces R and mu r obviously varies. And then only the force W and W force of the moment of the W about the point P. So distance of W from perpendicular distance from the point P is this equals to A sine theta, because this is the theta angle and this is the distance A. So obviously this is the perpendicular distance of the force W from the point P is A sine theta. A sine theta. So, and this is the anti-clockwise direction to the point P, about the point P. So this is positive. So W A sine theta. And the other force R dash, normal direction at the point this. So R dash, moment of the R dash about the point P. So the perpendicular distance of the force R dash from the point P is OQ. Obviously, OQ distance is the twice a cos theta, because this is the PQ is the twice A and this angle theta. So the right angle triangle POQ, we get the distance OQ is twice cos theta. And obviously, this is the moment, direction of moment, clockwise direction about the point P of the force R dash. So clockwise direction is negative. So obviously minus R dash twice a cos theta equals to 0. So obviously W is sine theta equal to R dash equals to mu r. So with mu r is also w. So mu w twice a cos theta, cancel w and a from both sides because both of them are non-zero value. So tan theta equals to twice mu is the correct answer. Correct option is 2. Next question E. For a rectilinear motion of a particle, if an impulse I changes its velocity from u to v and capital E is the change of kinetic energy, then the correct option is 2. E equals to I bracket E plus v by 2. Here, the impulse I equals to the change in the linear momentum. So mv minus mu. V is the final velocity, u is the initial velocity. So mv minus mu, changing the kinetic energy, changing linear momentum equals to the impulse is I, impulse I. So obviously m into v minus u. Now I u plus v by 2 equals to I means m into v minus u from 1, put the value of I m v minus u and u plus v by 2 by 1. So m by 2 into v square minus u square. So half m v square minus half m u square. So obviously half m v square minus half m square kinetic energy uh, at the final position and kinetic energy at the initial position. So change in kinetic energy, which is equal to E given this. E is the change in kinetic energy. So obviously this I U plus V by 2 equals to the change in kinetic energy E. Correct option is 2. Next question F. A particle moving along a straight line has the relation v square equals to 4 minus h square between the velocity v and displacement x from the origin uh, at any time t, then the motion is the simple harmonic motion if period twice by correct option is 3, which is repeated from 2021. So obviously v square equal to 4 minus v square, differentiating with respect to x. So twice v dvdx equals to minus 2x, cancel 2 from both sides, and then we get v dvdx is equal to dvdx dt square. The acceleration equals to minus x. So we know that dvdx dt square equals to minus mu x, where mu is positive constant. It's a simple harmonic motion if period twice pi by root mu. So comparing with this, here mu equals to 1. So this is the equation 1, represents the simple harmonic motion with period twice pi. Next question, G. A smooth sphere falling directly from a height capital H impinges on a horizontal fixed plane and rebounds to a height small h. And if E small e is the coefficient of distribution between the sphere and the fixed plane, then the correct option is small h equal to E square capital H. Here the answer is the from the sphere A from the point A from the point A smooth sphere falling directly from the height capital H to the point B in the horizontal fixed plane and rebounds the height up to CH, small h, up to this. So at the point A, the velocity is 0 and his velocity is the u before reaching the plane is velocity u. So u square equal to 0 square plus twice gh, and g is the acceleration due to gravity downwards. The particle falls in the downward direction, so g is the acceleration is downward direction, so both are positive. So u square equals to 0 square plus twice g capital H. So u equals to root over of twice g capital H. Is the velocity u, approaching velocity u. And by Newton's experimental law of impact, is v equals to e into u. V is the velocity after rebounds. So v equals to e into u, where e is the coefficient of restitution. And so v square equal to e square u square. And e square is this twice g capital H. So v square equal to e square twice g capital H. Now, from this position after rebounds, this velocity v, and at the point c, velocity is 0, and height is small h. So, in a particular is in direction, upward direction, but here g is downward direction, acceleration is downward direction. So here, final velocity 0 square equals to initial velocity v square minus 2g small h. Here minus because particle is in upward direction and g is in downward direction. So they are in opposite directions. So here minus sign here. But here u velocity particle is in the downward direction and g is in the downward direction. So here the plus sign is here. So small h is equal to v square by twice g, and this v square equals to e square twice g capital H. So put this value and e square into capital H. The correct option is 3. Next question, H. A particle describes the curve p square equals to AR under a force capital F to the whole. Then the law of force, its correct option is 3. A varies as r to the power minus 2. Middle equation of parabola p square equals to AR. Here, p square equal to AR, differentiated with respect to r, we get twice p dp dr equals to A, each constant. Here, and dp dr equals to A by twice p. Obviously, we know that from the central orbit, motion of central orbit, force A equals to h square by p cube dp by dr. So h square by p cube into dp by d equal to A by twice p. So A h square by twice p to the power 4. So p square equal to AR. So p to the power 4 equal to A square r square. So put this value p to the power 4 A square r square and cancel this. We get f equal to h square by 2a by r square. Means h and twice is constant, h square by twice is constant. So f varies r to the power minus 2. So f varies r to the power minus 2 is the correct option C. Next I, equation of the path in a central orbit r equal to a bracket 1 plus 2 cos theta. Then the apsidal distances are equal to, correct option is 2, 3a and a. Here, the polar form, central orbit path of the polar form is this r equal to a bracket 1 plus 2 sine theta bracket close. Differentiating with respect to theta, here d theta equal to twice a cos theta. And for apsidal distances, d theta equal to 0. So obviously twice a cos theta equals to 0, a non-zero quantity, so cos theta equals to 0. This gives theta equal to pi by 2 or 3 pi by 2. So when theta equal to pi by 2, we get the value of r is a bracket 1 plus 2 into sine pi by 2, which is 1. So 3a, r equal to 3a. And when theta equal to 3 pi by 2, and the value of r equals to a bracket 1 plus 2 sine 3 pi by 2. See 3 pi by 2 minus 1. So value of r is minus a. So actually magnitude of the distances are the apsidal distances are a and 3a. Correct option is 2. Question J, last question. A force capital A vector twice I cap minus G cap minus 2K cap acts on a particle located at the point P 0, 3, minus 1. Then the moment of the force A vector about the axis through O in the direction of the vector 3I cap minus 4K cap is, the correct option is 3. 3 by 5. Here, P is the point 0, 3, minus 1, and F is the force acting on the point P, and O is the origin. So OP is the R vector, and axis for O in the direction this 3I cap minus 4K cap. Here obviously OP vector equals to 0I cap plus 3J cap minus K cap, because coordinates of point P is 0, 3, minus 1. And F vector equals to giving that twice I cap minus J cap minus 2 K cap. Now the unit vector B cap along the line 3I cap minus 4K cap, we get B cap equals to 3I cap minus 4K cap by whole divided by root over 3 square plus 4 square, that is equal to 1 by 5 3I cap minus 4K cap. Then the moment of F about the line along B cap is given by this B cap dot R cross F vector. So this is the 1 by 5 component of B cap is this 3, 0, minus 4. A 1 by 5 common, and R vector 0, 3, minus 1, 0, 3, minus 1, and F vector is 2, minus 1, minus 2. After simplification, we get 3 by 5 is the answer of this. Thank you.